Hey everyone, this is Vijay. In this episode, I'm going to talk about one of the most fascinating stories in the history of science, and that involves regression. Yes, the same regression, the bedrock of all data science algorithms, perhaps the oldest. The year is 1917, and everything changed with the understanding of the universe. Albert Einstein releases the general theory of relativity, built on his earlier work, the special theory of relativity. He forever connected the space, the time, and the gravity, all in one grand equation. But the model he put forward also maintained the status quo, the prevailing understanding that the universe is static. Sure, the objects within the universe moved, but as a whole system, it is static. In fact, his equations predicted that the universe is dynamic, and Einstein has to introduce a special mathematical plug called cosmological constant to maintain the static state of the universe. As a whole, things are where they are. Universe is not moving, expanding, or contracting. Fast forward a few years. You can see the scientific process at work. Edwin Hubble and few others were unsettled by this concept of static universe, and they got to work. With his contemporaries, especially Lamarck and Slipher's scientific backing, he made startling observations of the cosmos. Let's put a pin on it. Before seeing what Hubble saw through the observations, let's take a detour. I want to introduce the concept of the Doppler effect. The speed gun used by a peace officer works because of the Doppler effect. Essentially, it measures the velocity or the speed of an object relative to a stationary object. When an object is approaching you, the light or sound wave is compressed. In the case of light, the object appears bluer because the wavelength is shortened. Vice versa, when an object recedes from the observer, the wavelength stretches and object appears redder than its natural color. This effect is useful because we can measure the speed and directions of stars and galaxies' movement. This is what Edwin Hubble saw in 1929. Edwin Hubble made observations of 24 galaxies and found something remarkable. Here is his 1929 paper, and I have plotted the chart based on actual data published by Hubble. X-axis is the distance of the galaxies from us. Y-axis is the velocity of the heavenly object. Even though there is no perfect correlation, you can clearly see as the distance of the galaxies from us increases, the velocity of the galaxy increases as well. What this means is the universe is expanding. This is the first observational evidence that can support the theory of expanding universe, and our static understanding of the universe is thrown out of the window. In fact, as you can recall, Einstein's general theory of relativity predicted the expanding universe, if not for that cosmological constant, of which Einstein later admitted is his biggest blunder. But he was in a way right, even though he was wrong. Of course, that's Einstein we're talking about. Moreover, Hubble's observational data used in the paper is a bit incorrect. Later observations confirm the same expanding effect, but with more accurate data, like the one you're seeing here. Let's break it down. Imagine you're baking bread, which has raisins or olives in it. You put a ball of dough, let's say 20 centimeter in diameter, mixed with raisins in the oven. 2 raisins inside the bread is at 5 and 10 centimeters from the center raisins. As the bread heats up, the dough expands to 40 centimeter. Now the 2 same raisins are at 10 and 20 centimeters from the center. More distant the raisin is, faster it moves from the center. Now we know why this chart conveys the concept of expanding universe. This is one of the most pivotal moments in our study of the universe. Let's see if we can generalize an equation to relate distance and velocity using the most used modeling technique, the humble linear regression. We're going to use the observational velocity and distance data and create a model y is equal to ax plus b, or generically velocity equal to a constant multiplied by distance. The constant is also called as Hubble's constant. Let's use Hubble dataset. And the modeling technique, let's fire up RapidMiner. Let's use Hubble dataset. This is how the data looks like. We have about 20 observations with galaxy names, distance from us, and velocity. We'll use set role operator to let RapidMiner know the roles of each attribute. First, the galaxy name, we don't need it, so I'm going to set it as ID. And the next one, velocity, is what I'm going to predict. So I'm going to have it as label. Now our process is ready to accept a modeling operator. We're going to use linear regression. We're going to leave the default parameters and run the process to find the coefficient for distance. And the value is 79. This is Hubble's coefficient. Generally these days, the value is found to be around 73. Let me indulge you with a fun deduction. If we do know the rate of expansion and where things are now, we can estimate how long this dough has been baking. Take this dinner roll. It was smaller a minute ago, even smaller 2 minutes ago, and you keep going until you get to the initial state. In real world, if we take the inverse of Hubble's constant, we can figure out when universe was in its initial state. Yes, we are talking about the singularity, the Big Bang event. Assuming the expansion is linear, we can calculate the age of the universe. For example, if I know the distance between San Francisco and LA is 400 miles, and if I drive, let's say, 50 miles an hour, it would take about 8 hours to complete the journey. Hubble's law is velocity equal to 73 times the distance. The unit of Hubble's constant is the inverse of time. So if we take the inverse of Hubble's constant, we get time, the age of universe, also called as the Hubble's time. That works out to be 4.2 10 to the power 17 seconds, which is 13.4 billion years. These days, the generally accepted age of universe is 13.8 billion years. It's quite close. A handful of observations and regression modeling leads to the age of the universe. That's quite something. Let's go back to RapidMiner process to calculate age of the universe. And next step is to convert this model into an example data set so you can perform additional arithmetic. To convert this to an example data set, you have to use a converter operator, which is available under RapidMiner Marketplace extensions. And I'm going to make use of this operator called linear model into example data set. The output is going to be very similar to the modeling operator, except the fact that this is an example data set. So under the attribute name coefficient, you find 79. And we can add additional attributes as a function of this coefficient to calculate the age of the universe. To do that, I'm going to get generate attribute operator and add a few more columns to the example data set we just saw. Number one is inverse. It's 1 divided by the Hubble's constant, which is under the attribute name coefficient. Now you can see the column inverse, which is inverse of the 79. This is still in kilometer per second per megaparsec unit, so we need to convert this into seconds. So let's go back and add one more attribute to find age of the universe in seconds. I'm multiplying inverse by 3.09 10 to the power 19. This should give me age in seconds, but we need it in billions of years. So let's start with age in years. There are 3.16 10 to the power 7 seconds in a year, so we just need to divide this. Let's add one more attribute, age of the universe in billions of years. That's it, and run it. So the age of the universe is 12.4 billion years based on this dataset. A couple of closing thoughts. Based on the discovery made in 1990s, we now know the universe is not just expanding, but the expansion itself is accelerating. So we have to use nonlinear models to determine the age of the universe. Number two, there is nothing new about the discipline, what we now call as data science. It's a very old technique. We have been using this trick for hundreds of years. Thanks for listening.